Okay, so in this section we are going to try to quantify how does the pressure in a fluid vary with depth. Right? As you go deeper and deeper in a fluid, does the pressure change and by how much? So first, let's just think about this. Let's just take a look at some water towers, think about some engineering. If you look at a bunch of different water towers, including one at Disney, we can see that all three of these look like they're made of maybe some wood paneling or maybe a thin metal sheet or something, and then there are these metal rings supporting the outside of each water tower, giving it some structural support. So looking at those metal rings, what do they tell us about water pressure? All right, so take a moment and think about that. And I think you can see that the metal rings seem to be getting closer and closer together as we go further and further down the water tower, deeper and deeper into the fluid, right? All of these water towers have metal rings that get closer and closer and closer, right? So it looks like for some reason you need more support at the bottom of a water tower than you do at the top, okay? And why is that? Well, we're going to find that the pressure of a fluid increases with depth, so therefore the amount of force on the outside of this container is going to be increasing with depth. Right? And I think this is something everybody has felt before. If you've ever gone swimming, I'm sure you've felt that if you swim too deep, you feel some pain in your ears. Right? That is the pressure of the fluid increasing with depth. Okay. So to better understand this and to kind of try to quantify it, we are again going to use one of these PhET simulations. So I really encourage you to again click on this link in the attached slides and go and play around with the simulation. But okay, let's try the simulation. So here I have a pool of water and I have a pressure gauge which I can put at different locations. So I could put it right at the top of the fluid, and you can see that the top of the fluid is exposed to the atmosphere and the pressure at that location is 1 atmosphere, or I could put it in SI units. It's about 101 kilopascals. Okay, so about 101 kilopascals at the surface of the fluid, or the equivalent of 1 atmosphere. Okay, as I go deeper and deeper, and let me add in a grid here. So I have 0 meters deep, 1 meter deep, 2 meters deep, 3 meters deep. As I take this pressure gauge and go deeper, you can see that the pressure in the fluid is increasing, right? And from 0 meters deep for 1 atmosphere to 1 meter deep, we increased by almost 0.1 atmospheres. If I go down another meter, the pressure has again increased by almost 0.1 atmospheres. We're close to 1.2 now. If I go down another meter, the pressure is now increased by almost 0.3 atmospheres. The pressure is close to 1.3 atmospheres here, or is close to 1 atmosphere at the top. So that not only is the pressure increasing as I go deeper, but it appears to be increasing in a linear fashion, meaning the amount that it increased from 0 to 1 is about the same amount that it increased from 1 to 2. Right? It seems to be increasing linearly. Right? So that's the first observation. If I measure depth, or the distance from the top surface of the fluid down, the pressure seems to increase linearly as I go deeper. Okay. We can also make a few other variations. We could say, instead of on Earth, what if we were on Mars? If I went to Mars, the force of gravity would be smaller, and if I can see that the pressure in this fluid also seems to depend on the force of gravity. It depends on lowercase g, right, the acceleration due to gravity. If I was to go to Jupiter, the pressure is much larger than Earth, right, and that is correspondingly bigger. The pressure at some depths in a fluid is correspondingly larger also. Right? So it appears that the pressure in a fluid depends not only on the depth, and it also depends on the pressure of the surface. It also seems to vary with the force of gravity. Okay, I can also vary the density. So right now I have water. If I used gasoline in this pool instead, the density is smaller, and the corresponding pressure is also smaller. So it appears that the pressure at some depths depends on the density of the fluid. If I filled this with honey, the pressure would actually be larger. Right? It's 1.2 atmospheres now because honey is more dense. If I put it back with water, it's now 1.16 atmospheres. So the pressure seems to also depend on the density of the fluid. And finally, earlier I had 1 atmosphere at the top, and I can actually turn off the atmosphere. Okay, now I have no atmosphere. I'm on the moon, right? Now the pressure at the top is 0 atmospheres, and if I go down 1 meter, the pressure is now somewhere around 0.1 atmospheres. Well, if I turn on the atmosphere, the pressure is now 1.10 atmospheres. So what that means is that the pressure at this depth depends not only on how deep you are in the fluid, but it also depends, the pressure of the surface also matters, right? Maybe I can make that more clear. Maybe I'll put this in some English units. So now it's 14.7 psi at the top. If I go down 1 foot, it's 15.2 psi. But if there was no atmosphere, the pressure at the surface would be 0 psi. And if I went down 1 foot, the pressure is only 0.44 psi. Right? So just turning the atmosphere on and off, changing the pressure at the surface, seems to change the pressure at every depth. Right? Even if I'm way down here at the bottom of the pool, if I change the pressure at the surface, you can see I'm drastically changing the pressure also at the bottom of the fluid. Right? So turning on and off the atmosphere, changing the pressure of the top of the fluid affects all depths. Right? So we're going to try to quantify that in a moment. The other important thing to note is if let me go back to metric units here. If I look at the pressure at a given depth and bottom of a pool, that seems to get bigger as I go deeper, right? There's some pressure there. Let me put it back to atmospheres. Okay, now what about the pressure on this side at the same depths? Is the pressure going to be bigger over here because it kind of looked like there's more water on top of me pushing down on me? Or is the pressure going to be the same? So let's check. So let me try to get it at about the same height. And okay, both of these pressure gauges are at exactly the same depth, and they're both rating exactly the same pressure. Right, so it looks like the dependence of pressure with depth does not matter what kind of container you're in, doesn't matter the shape of the container, all that matters is the depth. All right, so we've now learned a lot about how pressure depends on depth. Let's try to quantify that in a moment. And let me just also note that if I take some water out of this pool, what this means is that the water level in a pool is going to be the same on both sides of this, even though they have different shaped containers. Okay, so that was a lot of different things we've been able to learn about pressure. So let's try to quantify that now. What we learned was that pressure increases with depth, and that it depends on the pressure at the surface, and that it depends on the density of the fluid and the force of gravity or the acceleration due to gravity. Right, so we're going to have 2 ways of calculating this. The first way is if I draw a coordinate system where I've defined my coordinate system in our typical way where the plus y direction is up, and I have 2 different values of my y position, y1 and y2, I can measure the pressure difference between point 1 and point 2 using this formula. So the pressure difference, the pressure at point 2 minus the pressure at point 1 is equal to minus the density of the fluid times the acceleration due to gravity multiplied by the difference in the 2 y values of those two points. All right, so that's an interesting equation, but typically we're not measuring a coordinate system from the bottom of a pool. Typically we're measuring depths. We're measuring from the top of the surface down. So we're going to use this formula a lot more often. So if we define a coordinate system where we're just going to say the depth 0 is the top of the pool, and then we're going to measure down, and how far down is the depth, or symbol h. I know it's not the best symbol for depths, but that's what the textbook uses. So the pressure at this depth, P, is equal to P naught, the pressure at the surface, right? So that's just the pressure, whatever pressure is at the surface of the water. On Earth, it's typically going to be atmospheric pressure, plus the density of the fluid multiplied by the acceleration due to gravity multiplied by the depth. All right, so you can see that if I increase my depth, if I go deeper and deeper and deeper, I'm increasing the pressure. If I go to Jupiter and increase G, I'm increasing the pressure. Or if I increase the density, I'm increasing the pressure. Or if I'm increasing the pressure at the surface, I also increase the pressure at every depth. Okay, so that's an important equation we're going to use a lot. So just to make sure we summarize this, symbol P is a pressure at a given depth. Symbol P naught is a pressure at the surface. Rho is the density of the fluid. G is the acceleration due to gravity, and H is the depth. How far down from the surface are you? We can see there's a linear increase in pressure as you go deeper, right? This depends on H, the depth. It doesn't depend on H squared or anything like that. So the pressure linearly increases as H increases. It also depends on the density. Greater pressure for a given depth at a denser liquid. So if I have honey, if I have a denser fluid, the pressure is larger at a given depth. Okay. Also, it also depends on G. So if I go to a different planet, the pressure at a given depth is going to change. And so this is going to be an important formula for solving problems. And in fact, in some cases, you'll get somewhat complicated problems like this one. Here I have a test tube filled with a whole bunch of different fluids. I have vegetable oil floating on top of water, which is floating on top of dishwashing liquid, which is floating on top of just some sugary syrup, which is floating on top of honey. Right? So these different fluids all have different densities, and they all have, therefore they're not mixing here, they're just floating on top of each other. So if I wanted to know what was the pressure at the bottom of this test tube, I would have to take all these into account. Right? I'd have to split it up into many different problems. First, I have to figure out what is the pressure at the surface. That is the atmospheric pressure. And then I have to figure out what's the depth of the oil. And I can figure out the pressure at the bottom of the oil just using the same formula. Right? So here we split it up into many different problems. So the pressure at point 1 here, at the interface between the oil and the water, is just the atmospheric pressure at the top plus the density of the oil times G times the depth of the oil. Right? That's this distance here. Right? If I want to figure out the pressure at point 2 between the water and the dishwashing liquid, to figure out the pressure at point 2, well, I need to know first the pressure at the top of that fluid, which in this case is not atmospheric pressure, it's just pressure 1, right? Because there's oil on top of the water. So if I know the pressure at point 1, I can figure out the pressure at point 2 just using the density of water, the G, and the depth of the water. Right? And I can keep doing that for each layer until I get down to the bottom. Right? If I want to figure out the pressure at the volume of the test tube at point 5, first I need to know the pressure at point 4 at the top of the honey. Right? Once I know that, if I know the density of the honey and I know the depth of the honey, I can figure out the pressure at the bottom. Okay, so that's a nice type of problem you may see. We can do experiments to kind of prove that pressure varies with depth. And a really common one is to basically have a bottle of water or a test tube and just put some holes in the side of it and see what happens. And you can see that the water coming out of this hole has some velocity and is going through some parabolic path here. The water coming out of this hole seems to be going faster, right? The projectile motion is traveling farther, and the water coming out of the very bottom is going even further. So it appears that the water coming out of the bottom is moving even faster, meaning the pressure at the bottom of this test tube is bigger than the pressure at the top. Right? The same thing you can see here with just this water bottle where you've cut some holes in it. And the water coming out of the bottom is shooting out farther because the pressure inside the water bottle is larger at the bottom. And you can quickly watch these videos. Oops, sorry, wrong web page there. Oops, there we go. So here is the first experiment where this person will you can see that the water coming at the bottom is shooting out faster and further than the water coming out the top, right? So that's a nice, interesting experiment. And we can see the same thing here with this water bottle. Okay, so the water coming out the bottom is obviously moving somewhat faster than the water coming out of the top. So the pressure at the bottom of the bottle is larger. Okay, so all right. Moving back to our presentation. So what we've learned is that the pressure in a fluid depends only on depth. It doesn't depend on the shape of the object. So at the bottom of this test tube, there's the same pressure at the bottom of this test tube. Even though this one seems to have has more fluid on top of you, it doesn't really matter. right? All that matters is your depth, right? Same thing here. The pressure at this depth is exactly the same as the pressure at this depth, right? Even though, again, there's more fluid on top of you. Or if you have a wider container, it doesn't matter. All that matters is the depth. Okay, this is really important. The fact that pressure is increasing with depth is important in the medical field. Right? Whenever you get your blood pressure read, they always do it on your arm, and they always are making sure you're sitting up, right, so that your arm is exactly at your heart level, right? Because if you were standing up and you measured the blood pressure in your legs, it would actually be larger, right? It's deeper. And so it's, in order to be kind of uniform everywhere, the standard reference point is measuring the pressure at heart level. Let's do a quick clicker question. If you have a cylinder which is completely filled with water, and if the top of the cylinder is sealed with a tight-fitting lid, if you were to push down on the lid with a pressure of 1,000 pascals, at the bottom of the cylinder, what happens? So you're increasing the pressure at the top of the fluid by 1,000 pascals. What happens at the bottom of the vessel? And the answer here is B. So if you increase the pressure at the top of a fluid by 1,000 pascals, you also increase it at the bottom of that liquid by 1,000 pascals. And that's, again, the equation we've been using will tell us that, but also we can use this simulation again. Maybe I'll turn off our grid. I'll keep the grid for now. So I have two different pools of water that are connected here. The water level is the same on both. And let me put pressure gauge on this side. If I put a weight on this side, you can see even over here I increase the pressure. Right? If I take the weight off, the pressure goes down. If I increase, so I'm increasing the pressure just on the top of the surface. Right? I'm applying some force on the top of that fluid, but I'm correspondingly increasing the pressure way over here. Right? So if you apply the pressure to the top of a fluid, you increase the pressure at every depth. Right? If I'm at the same depths on both sides, the pressure is going to change the same amount on both sides. Okay. And so again, you can play around with this simulation. It's kind of fun to play with. You can see also that the water level on this side had to go up. Right? On this side, the water level had to go up in order to make the pressure over here uniform. Right? Because again, the pressure depends on depth, and it depends on the pressure at the surface. Right? So over here, the pressure at the surface is larger, so I don't have to go as deep to get that pressure. On this side, the pressure on the surface is smaller, the atmospheric pressure, so I have to go a little bit deeper to get that same pressure. Okay, so that's it for this video.